Hi friends, welcome to learn fundamentals of data structures and algorithms course. We are discussing the performance analysis of an algorithm. We are discussing the space complexity and time complexity of an algorithm. In finding the time complexity of the algorithm, two methods are used. One is the step count method. Second one is a step table method or a tabular method. In the step count method, we have defined the global variable count, which is initially set to 0 for each executable statement or for each executable instruction. We have incremented the count by 1. Finally, we have determined the total number of execution steps. In the step table method, we have constructed a column algorithm, steps, step per execution, frequency, step per execution, star a frequency. We have summed the last column and then obtained the total number of execution steps. Of the given algorithm. The total number of execution steps of the algorithm in general depends on the input size, say n. Total number of execution steps depends on the input size n. For example, consider the array sum algorithm, in which we need to find this evaluation a1 plus a2 plus a3 plus etc. an. We have obtained a t sum of n is equal to, say, a 2n plus 3 steps. T of n, T represents the computing time of an algorithm, time complexity. N represents the input size. The total number of execution steps of the algorithm is, for example, a 2n plus 3 steps. In this case, the right hand side expression, this involves the input size n. N is involved here. Now, for large value of n, how to represent the computing time of an algorithm? That is our question. For a smaller value of n, no problem, right? So, n is equal to 10. We can say 20 plus 3, right? 23 steps are required. N is equal to 100. 203 steps are required. When n is equal to 1000, 2003 steps are required. Likewise, when n becomes larger and larger, how many number of steps are required? That we can easily find, right? Substituting the value of n, we can find the total number of execution steps. But the question is, when n becomes larger, how to represent the complexity of an algorithm? For large input size, for large input size, what is the performance of the algorithm? How to represent its computational complexity? For large input size, in general, we need to ignore the lower order terms and consider the highest order term. In the highest order term, ignore the multiplicative constants. Ignore the multiplicative constants. So that in 2n plus 3, say f of n is equal to 2n plus 3, in which the lower order terms, say 3 is ignored, only the highest term is 2n, in which the multiplicative constant 2 is not to be considered. Considering only the highest order term n, that represents the computing time of an algorithm, right. So, conveniently we can represent the computing time using this highest order term n, which represents this is a linear computational complexity. So, for large value of n, or we can say when the input size n becomes larger and larger, or n becomes infinity, the performance of an algorithm is represented as a linear computational at time. For that, we need some convenient notations. The convenient notations are asymptotic notations. Asymptotic notations represent the computing time of an algorithm. There are different asymptotic notations. So, before going to see, right, the different asymptotic notations, just see, right, this concept. Suppose consider a curve y is equal to f of x. Now, consider the point, right, P, at which we need to draw a straight line like this. Suppose a straight line coincides the curve y is equal to f of x at this point P, then clearly, right, this P, right, is the point that meets the curve y is equal to f of x. So, this straight line is said to be the tangent to the curve y is equal to f of x. We need to find the tangent to the curve y is equal to f of x for large input sizes. Suppose n represents the input size of an algorithm. When n becomes larger, we need to find the straight line that meets the curve y is equal to f of x. The curve, right, y is equal to f of x meets the straight line only at larger value of n. For example, when n reaches a plus infinity, we can say the straight line becomes the tangent to the curve, y is equal to f of x. So, we need to find the straight line so that the straight line meets the curve, right, y is equal to f of x for larger value of n, so that the corresponding tangent to the curve is obtained. So, just think of y is equal to f of x in terms of total number of execution steps. Total number of execution steps of the algorithm. When n becomes larger, we need to represent its computing time using the highest order term in the total number of execution steps. For that, right, we have several convenient notations. We need, right, the asymptotic representation, using big O, big omega, theta, small o, small omega, this is small omega and small o. These are the asymptotic representations or asymptotic notations. Using these notations, we can represent the running time of the algorithm. For large input sizes, conveniently we can represent the running time of an algorithm. Big O, right, this is big O. Second one, this is big omega. Third one, this is theta. This is small omega and this is small o notation. See what is asymptote. Asymptote means a straight line that continually approaches a given curve, but it does not meet at any finite distance. So, clearly when the straight line becomes the tangent to the curve, then we can say that the straight line is said to be asymptote to the curve y is equal to f of x. Since we are discussing for larger inputs, we can say the straight line becomes the tangent to the curve only at infinity. That means when the input size n becomes infinity, we can say the straight line becomes the tangent to the curve y is equal to f of x, right. That is actually the asymptote to the curve y is equal to f of x. So, asymptote is a straight line that continually approaches a given curve. For example, this is a straight line. In case if you like to draw a straight line like this, the straight line will never touch the curve y is equal to f of x at finite distance. That means when the input size n becomes larger, when n becomes plus infinity, that stage the curve, right, y is equal to f of x is closer to the curve, closer to the straight line, that stage, right, we can say the curve y is equal to f of x coincides with the straight line only at n becomes plus infinity. That stage the straight line becomes the tangent or asymptote to the curve y is equal to f of x. So, here our concept is how to represent the running time of an algorithm for large input size. For that, we have the different asymptotic notations, a big O notation, big omega notation, big theta notation, small omega notation and small o notation. Why do we need these asymptotic notations? The asymptotic notations are required because these notations describe rate of growth relationship, rate of growth relations between the functions. Asymptotic notations describe the efficiency of an algorithm, Asymptotic notations help in determining the best possible algorithm. That means to compare the performance of various competing algorithms. Suppose P is the given problem to be solved. Assume we have n different algorithms A1, A2, A3, etc. An. Each algorithm's computational time should be represented using the asymptotic notation. Then we can find out the best possible algorithm among all these competitive or competing algorithms. So, to compare the performance of different or competing algorithms and to identify the best possible algorithm, we need asymptotic notations. Asymptotic notations describe how the function behaves or how the function grows for large input size, let it be n. When n becomes larger, the performance of an algorithm rate of growth relationship is obtained using the asymptotic notations. Using the asymptotic notations, we can represent conveniently the computing time of an algorithm. There are some typical running time functions available, typical running time functions. Big O of 1, this is to be a constant running time function. Big O of log n, this is the logarithmic computational function. Big O of log star n, this is the iterated logarithmic computational function. Big O of log n whole power c, this is polylogarithmic computational complexity. Big O of n, this is said to be a linear complexity. Small O of n, this is a sublinear complexity. Big O of n into log n, this is log linear or quasi linear computational complexity. Then order of n square, this is quadratic computational complexity. Order of n power 3, this is the cubic computational complexity. Order of n power c, where c is greater than 1, this is said to be the polynomial or algebraic computational complexity, order of n power c. Then order of c power n for the constant c is greater than 0, this is said to be exponential or geometric computational complexity. Order of n factorial, this is the factorial or combinatorial computational complexity. Order of say 2 power c power n, this is said to be the double exponential computational complexity. These are some typical running time functions. Whatever the algorithm, right, we are designing, right, the algorithm's computational complexity can be any of these typical running time functions. For example, the array sum algorithm, we have obtained t of n is equal to 2n plus 3, 2n plus 3 which results in ignoring the constant and taking the highest term, order term, and ignoring the multiplicative constant. This results in big O of n, that means a linear computational complexity. Now we like to focus on the different asymptotic notations. In this session we focus on the different asymptotic notations. The different asymptotic notations are big O, then big omega, this is the theta, then small omega, then this is small o notation. A big O, right, this is asymptotic upper bound. Asymptotic upper bound notation. Big omega, this is said to be the asymptotic lower bound notation. Theta, asymptotic tight bound notation. Small o, asymptotic upper bound, that is not asymptotically tight. Small omega, asymptotic lower bound, that is not asymptotically tight. These are the different convenient notations which are used to represent the running time of any algorithm. In general, the running time of an algorithm is represented conveniently using the big O or a theta notation. Now let us explore these notations. First one, a big O notation. Big O notation is represented using this symbol, a big O. A function f of n is said to be big O of g of n if and only if there exists positive constants c and n0 such that f of n is less than or equal to c into g of n for all n greater than or equal to n0. So, taking the two functions f of n and another one is c into g of n, or you can take right a function g of n. Taking two functions f of n and g of n, when is f of n said to be big O of g of n? We need to find right two positive constants c and n0 such that this inequality should be satisfied. F of n is less than or equal to c into g of n for all n greater than or equal to n0. Since f of n is less than or equal to c into g of n, we have 0 less than or equal to f of n. F of n, right, this should be greater than or equal to 0. Pictorially, consider this representation. This is c into g of n. This is f of n. Consider this intersection point. This is n0. Here input size is taken in the x axis n. Clearly, after this right intersection point n0, we can find right f of n is less than or equal to c into g of n. So, before the point right n0, right, the relationship may not be satisfied. So, since we have drawn the representations of f of n and c into g of n pictorially, n0, right, this is the intersection point. After this point, when the input size n is greater than or equal to n0, the relationship f of n less than or equal to c into g of n is satisfied for all n greater than or equal to n0. So, f of n is said to be big O of g of n. That means f of n is equal to big O of g of n, or we can write f belongs to big O of g. F of n is equal to big O of g of n, or f belongs to big O of g if and only if there exists two positive constants c and n0 such that f of n less than or equal to c into g of n, this should be satisfied for all n greater than or equal to n0. In that case, right, we can say g of n is an asymptotic upper bound for f of n. G of n is an asymptotic upper bound for f of n. So, considering these functions f of n and g of n, we can say set of all functions whose rate of growth is the same or lower than that of g of n. Set of all functions which are represented as f of n. Seeing the graph, right, the set of all functions say f of n whose rate of growth, this is the rate of growth, the rate of growth is same or lower than that of g of n. F of n rate may be equal to f of n is equal to c into g of n, or f of n is less than c into g of n. In that case, we can say the rate of growth relationship results in the asymptotic upper bound for the input function f of n. So, g of n is said to be asymptotic upper bound for f of n if and only if f of n is defined as big O of g of n, that is f belongs to big O of g. Consider this relationship f of n is less than or equal to c into g of n for all n greater than or equal to n0, 0 less than or equal to f of n. In this case, since g of n is an asymptotic upper bound for the f of n from the factorial representation, right, this is the function some constant into g of n. So, c into g of n, in which the function g of n determines the asymptotic upper bound for the function f of n. In that case, when applying the limit to this inequality, we have limit n tends to infinity f of n by g of n, this is equal to a constant, the constant is less than infinity. So, when limit n tends to infinity, f of n by g of n is equal to constant, and the constant, right, which is less than infinity, we can say f of n is equal to big O of g of n, that is this is represented as f belongs to big O of g. We can say g of n is an asymptotic upper bound for the function f of n. For example, consider the function f of n is equal to 3n plus 2. The function f of n is equal to 3n plus 2 can be represented as 3n plus 2 is less than or equal to 4 into n. If you take, right, f of n as 3n plus 2 and g of n as n, f of n is equal to 3n plus 2, constructing the column for 4n, n represents the input size. When n is equal to 1, 3 plus 2, right, 5, here 4 into 1, 4, 5 is greater than 4. N becomes 2, 3 into 2, right, 6 plus 2, 8, 4 into 2, 8, equal relationship. When n is equal to 3, 3 into 3, 9 plus 2, 11, 4 into 3, 12, 11 is less than 12, 4, 14, 16 less than 5, 17, 20 less than. So, hereafter when n becomes higher, the relationship, right, less than holds hereafter, right, less than relationship. Here only equality relationship. So, the intersection point is this n is equal to 2, right. So, the relationship 3n plus 2 is less than or equal to 4n for all n greater than or equal to 2, which means n0 is equal to 2. When n0 is 2, both 3n plus 2 and 4n are equal. After that, the relationship is changed. completely 3n plus 2 is less than 4 into n. Hence, we can write f of n is less than or equal to c into g of n for all n greater than or equal to n0. f of n is 3n plus 2 is less than or equal to 4 into n for all n greater than or equal to 2. This implies f of n is equal to 3n plus 2, g of n is equal to this one n, and n0 is equal to 2. Since f of n is less than or equal to c into g of n for all n greater than or equal to n0, the relationship or inequality is satisfied. We can say f of n is equal to 3n plus 2 is equal to big O of g of n. Big O of g of n is n. So, 3n plus 2, right, this results in big O of n, that means a linear computational complexity. Second example, consider this f of n. N represents the input size. F of n is equal to n square plus 2n plus 3. Considering g of n is equal to n square, let us try to write this as n square plus 2n plus 3 is less than or equal to 2 into n square. Fixing the columns n square plus 2n plus 3, 2n square n, when n is equal to 1, 1 plus 2 plus 3, 6, this is 2, 6 is greater than 2. When n becomes 2, 4 plus 4 plus 3, right, 11, here 8, 11 is greater than 8. When n becomes 3, this is 18. What happens? 9 into 2, 18. 18 is equal to 18. When n becomes 4, 27, 32. 27 is less than 32. When n becomes 5, 38, this is 50. 38 is less than 50. So, hereafter, right, whichever the value of n, this less than relationship is satisfied. Only when n is equal to 3, the equal relationship is satisfied. So, we can write n square plus 2n plus 3 is less than or equal to some constant, right, we assumed the constant c is equal to 2 into n square. In the previous example, right, what is this 4? We are assuming, right, the constant, right, c is 4. Since we would like to satisfy this inequality, f of n is less than or equal to c into g of n for all n greater than or equal to n0. The constant is, right, taken as a positive 1. N square plus 2n plus 3 is less than or equal to, taking one constant, right, c as 2, we can write 2 into n square for all n greater than or equal to 3. Now, this representation is in a form of f of n is less than or equal to c into g of n for all n greater than or equal to n0. That is f of n is equal to n square plus 2n plus 3. What is g of n? C into g of n. it seems g of n is n square, constant is 2, n0 is n greater than or equal to 3. So, n0 is 3. Since n square plus 2n plus 3 is represented in this form, f of n is less than or equal to c into g of n for all n greater than or equal to n0. This implies f of n is equal to big O of g of n. That means f of n is equal to big O of g of n is n square. That means the given function f of n is equal to n square plus 2n plus 3. This results in a quadratic computational complexity. How to find? In short, given the total number of execution steps, let f of n represents the total number of execution steps of the algorithm. We need to find the big O or computational complexity. For that, we need to ignore the lower order terms n square plus 2n plus 3. The lower order terms, right, 3, 2n are ignored. The highest term is n square, in which multiplicative constant is 1. So, 1 into n square simply n square. This results in big O of n square computational complexity. So, f of n is equal to n square plus 2n plus 3, which results in n square, a quadratic computational complexity.